So let me get started. So the discussion is about the modern approach to SoC verification. And the way that we split is the what and why. That'll be something I'll cover, and then Louis will go over the how. So we all know that chiplets are revolutionizing the whole system design. It's become a cliche right now. And chiplets are the new building blocks of computing. But the main aspect over here that I want to touch on is the modernization of shift left that I'm going to be looking at, which is, as you all know, AI needs to be looked at as a full stack. What I mean by that is it's not just the hardware, it's the firmware and the software components together needs to be looked at. And for that, we need to make sure that we have an aggressive shift left. And this is because we need to have a competitive advantage with things that are churning out from the AI industry. Things get obsolete pretty soon. So what we need for that is three components. We need a pre-verified compute subsystem, an early software optimization to be done on those, and of course, the combination of both, which is the co-validation of the software and hardware. Yes, these things are happening right now, but there are aspects that I'll be talking about that give some credence to this aggressive shift left. And of course, all of this is under the open standards of FCSA, which is our foundation chiplet system architecture that we just released to OCP, the AMBA-CHI, and it's all part of the OCP interoperability guidelines. Currently, we have the shift left taken care of, and this was announced at OCP August 2023 of our ARM Neoverse compute subsystem, which is by far the fastest path to production silicon, and it has proven for partners where they have saved resources and also time and accelerated the time to market. And that being said, it's also the world's leading performant subsystem out there, and it is based off and built on the leading edge technology. Now, this creates the shift left of the optimized compute system, but not yet. We are talking about the full stack that I just mentioned. So what it is, we are trying to compress the time to market from the AI competitive advantage for our partners. So currently we have the IPs, we go to the development approach with the virtual prototyping, which helps with the software development, and then we go into the system integration. We do some shift left, but it helps with the software development acceleration. But no, we need more. So this is where the ARM CSS comes in, and along with that comes our ecosystem collaboration via the ATD ecosystem that we have, where our leading vendors, the supply vendors and the EDA vendors are part of this ecosystem where they collaborate with ARM and integrate their IPs and their flows to basically accelerate the silicon development timeline with the co-validation piece and the software development all happening together and accelerating the entire development cycle. So this is what we call the modern shift left approach via the optimized CSS plus the ecosystem collaboration that we have via ATD folks. So what does it do? So where we are is we have the CSS, which provides the integrated and validated subsystem. But then with the ARM Total Design ecosystem play, we get an optimized CPU chiplet, which, if you see, is now going to play good with this AI full stack. And this is the acceleration that we are talking about that is coming to fruition. And the next few slides, Louis will be talking about the collaboration that Siemens has with ARM towards this modern approach. Thank you.
All right. Hello. Can I have the clicker?
Oh, sorry.
It's all right.
I just embellished that.
Thank you. All right. Hi, everyone. I'm Luis Rodriguez from Siemens EDA. And we've been thinking about shift left for a long time. It's no secret that, ASIC first-time silicon success has been going down, and the, ASIC projects behind schedule has been going up. The CSS is looking to address this, of course. But we've been thinking about shift left for quite a while, and we've had some success with it in spaces like the SSD market for NVMe, where firmware is very critical to SSDs, as well as CXL. And so based on the success we've had in the SSD market, we're bringing this to the ARM ecosystem through the ATD partnership. And the basic building blocks are, starting from standards-based verification IP. So my team has been doing verification IP for over 20 years. It's all standard-based, so things like AMBA, CHI, AXI streaming, low-power interface, but also PCI Express, CXL models. These are fully SystemVerilog class-based VIPs that can be dynamically configured. You can use them for error injection. You can randomize behavior to get high coverage. And so they're typically used at the IP level. But now we want to bring it into the system level, at the CSS level. And the way we do that is through System C integration through TLM. And so we're able to build an adapter or shim layer to the VIPs that can connect to an ARM fast model. And so now we're able to bring this ARM fast model. So here you have a CSS with, it's a little bit abstracted away. You can see the main blocks like the CMN, the IO macro block. And just based on what I was showing in the previous slide, we can now bring the ARM fast model into a simulation. So on the right, you have RTL code. The block that just appeared, that's the one I was showing before. You have an ARM fast model through TLM ports connected to verification IP. And then we can keep building this out. We have the infraboard FVP here, very similar, connected through TLM to the AXI VIPs. And you can connect things like we have a PCI Express subsystem that's pre-validated, SBSA compliant, built again. This is the SystemVerilog VIP with some additional adapter code. And so at this point, you're actually able to load UEFI and UEFI image, do the whole boot up process, start running test cases like SBSA, and prove that your system that you might have configured differently from the out-of-the-box test bench. So you have made some configurations. This allows your firmware team to start validating firmware. It also allows you to run SBSA test cases and other interrupt test cases. And then, of course, at this point, you might have other teams that are working on, for example, PCI Express IPs at the block level, and they can start also substituting VIP for IP blocks and take a modular approach to bringing up your CSS. You can also model multiple chiplets, through PCI Express or UCIe. And again, you can use a combination of IP and verification IP to model this. And there's multiple advantages, of course, doing this shift left approach. It allows your firmware teams to start working earlier on the firmware. It allows your hardware team to collaborate with the firmware team during the debug. So you're running RTL simulations. You can do waveform dumps. You can do step-through debug. So we do support setting breakpoints in the firmware or software, and we will pause the RTL simulation. And so you can do step-through debug. And it runs faster than you might think. We've done a lot of optimization to this software-aware VIP. And so right now, we're able to run about 800 million instructions, which is about as much as it takes you to get to UEFI in less than 2 hours. And you can just see an example of dumping out a tarmac trace. And on the right, you get the verification IP tracker files that show you information at the FLIT level. And Yes, so do you want to do the call to action?
Sorry. So there's a call to action for contribution towards this shift left flow that I just presented. If you see something that is inherent that is not there, called out, please let me know. And other than that, there is a BSA, SBSA compliance program that we have, pre-silicon compliance program. So please do contribute to those. And as I just mentioned, we provided the FCSA spec to the OCP community, so requesting contribution towards that.
All right. And additionally, we could not bring this shift left methodology without a lot of the open standards. So we've collaborated to PCI Express, CXL, UCIe specs, a bunch of wires as well. It requires things like contributing to QEMU as well for specific applications and being able to also debug the open source UEFI code. So all of these pieces are brought together into this methodology. And finally, we're very open to partnerships, and so you can reach out to us either through the ATD partner program or directly. Thank you.
Thank you.